Okay, we've dealt with separable equations. When you see this equation, you see it's not linear. You got a square root of y there, okay? And you can't use any of the techniques that we developed except try to separate it. So you can easily separate it. You get square root of y dy equals 1 minus t squared. Okay? And then that's times your dt. And that's very straightforward if you see it. The reason you might not see this, and of course separability is something you always want to look at because that usually makes the problem easier than it would be through any other technique. What you see here kind of looks like maybe, you know, is it first order linear, or is it, you know, you got to, you know, you first see this and you think, well, if I had a y there and something else there, but no, you got a square root of y, there's nothing to do. Okay? So, try the separability and boom, it works. Okay? And then of course, let's go ahead and finish it. So you integrate this. And antiderivative of y to the 1/2 is 2/3 y to the 3/2. And over here you're going to get t minus t cubed over 3 plus a constant. And then you do your y to the 3/2 equals then 2/3 t minus, it's not 2/3, it's 3/2. 3/2 t minus t cubed over 2. Again, your arbitrary constant absorbs the multiplication by 3/2. And you get y that equals 3/2 t minus t cubed over 2 plus c to the 2/3. Okay? There it is. Now, if you have initial conditions, like let's put an initial condition on this, like y of 0 equals 8. Okay? And actually, let's make it 4 so we get an integer. Okay? So what do? You say, okay, y of 0 equals c of 2/3, plug in 0 for t, you get 2/3, so c to the 2/3 equals 4, c equals 4 to the 3/2, which is 8. So now your solution is okay? Very straightforward, just got to remember to do all the steps. Okay, now there's another situation, something I love to do, physics and pre-calculus classes. I don't see the bottle. Yeah, I do. We take this bottle here. It has a tube sticking out of it. Fill the bottle with water. Water's going to flow out of the tube. Okay? So if the thing is full and you got your finger over the tube so it's not leaking, fill it up, let it go. We've got marks there. We can observe where the water is versus the time that's elapsed. It turns out you get a quadratic function. Depth is a quadratic function of time. And it's very, very accurate, okay? And this deviates from quadratic by something that is really difficult to even see. okay? Now, what's going on? Well, the deeper the water is, the more pressure there is, okay? So you got this bottle, nice symmetric bottle, and you got water in it. It's actually a uniform cylinder, okay? So you got water and there's a shark's fin to make sure you understand that it's water, okay? And you got the outflow tube. And this distance is going to be Y. Okay? Pressure just deciding how much physics I want to do. Okay, I'll do it. We'll suppress the units. Pressure is approximately 10,000. It's actually 9,800. Varies from one point on the Earth to the other because of different acceleration of gravity. But it's all pretty close to 9,800. We'll just say 10,000. Okay, it's 10,000 newtons per square meter times Y. It actually, okay, pressure comes out in newtons per square meter, and Y is measured in meters. Okay? So when you multiply this by Y, you get newtons per square meter, and that's pressure, force per unit of area. Okay? Whether you understand that or not, I mentioned it. Just to convince you at least that there's hard physics behind this process. Okay? And then conservation of energy in a way that you probably won't understand if you take physics implies V exit. That's the velocity of the water that comes out of here. You get some velocity of exit. Is square root of two times the pressure over 9.8 meters per second squared. I've got to scribble something down here to make sure I'm right about that. So you're going to have 1/2 rho v squared equals pressure. So yeah, and it's not over this, it's over density. That was kind of stupid because gravity's already accounted for in pressure, and it would have been really bad. Okay, so it's this. So this comes out to be approximately square root of 20Y. And now I'm suppressing units. Y is in meters. This will be in meters per second. Okay? Now that's just physics background. This is simple geometry that nobody ever understands because nobody ever has a geometry course when they come here. They got a course called geometry, but they don't have a geometry course. Total idiocy, in my opinion, on the mathematics education establishment.
I think he did a pretty good job on that.
Huh?
Professor Gallier spent a decent amount of time with this part. Like, yeah.
Yeah. But if you don't have a good course in solid Euclidean geometry, you're not going to understand very well. Or, yeah, maybe you will, because you guys are really bright, but you know, most people will not understand, and most physics students, engineers, go on to do well, still can't grasp it. The rate of change of the depth is assume it's exiting through a tube. This is the cross-sectional area of the tube. It's really a cylinder. I didn't draw a very good cylinder there. But you don't know how it's shaped on the other side, so maybe it still has a uniform cross-sectional area. Something with a uniform cross-sectional area, okay? Wouldn't necessarily have to be a cylinder, it could be a corkscrew. Can you do a corkscrew with uniform cross-sectional area? Yeah, geez, if I only had some geometry. Okay, so, you have this, okay? And it just says that the speed that water comes out here, well, any water that comes out here is water that's lost up here. If you take the area of this to the area of this, you have a ratio that gives you information about how fast this goes, if you know how fast this is going. Okay? Just continuity equation. I just don't understand why people talk about a continuity equation. It's something so obvious. I'm sure there are fluid dynamicists who would say, well, you can do this and this and this. And I've seen stuff, so yeah, you know what I'm talking about. Okay, so anyhow, you got this, right? Well, so rate of change of depth is dy dt equals B exit times this ratio, whatever it is, and that's it. Of course, V exit is the square root of 20y. So the dy dt equals, I'll use capital R. Times the square root of 20y. And R is your area ratio. So if this tube has 1/1000th cross-sectional area of the cylinder, that's at 0.001. Okay? Okay. That's a separable equation. So, solve it.